Um, I have some announcements. Firstly, there's a new handout at the front. Apparently, I printed too many because no one's here. And today only, I have to move my office hours from whenever they normally are, which is I think 2 to 3, but maybe 3 to 4. Whatever they normally are, today they're 4 to 5. And they're in my office, which is DL406, okay? So if you were coming by today, you have to come by then. I have taken the results from the Get to Know You survey, and people's majority want their midterm to be in class. So I figured we should work out when it should be together, because I don't care, to be perfectly honest. So what's pertinent for you all is midterm is on the 28th, and I think that's the deadline for dropping the class without getting a W on your transcript. So I think I probably need to get your midterm back to you before this, the first one, right? But also there's just no class October 20th because of fall recess. Okay, so that's the Thursday before. So what do we think? Do you want the Tuesday before fall recess? Do you want the week before fall recess? No one cares? Tuesday before? So the thing with I'm fine with it being the Tuesday before. The thing is that people do this thing where, like, if fall recess starts on Wednesday, they get a flight booked on Tuesday. And then they're like, oh, I booked my flight. What can I do? I'm like, I don't know. Maybe don't book your flight during class time. Okay, so I can do this, but that does limit your ability to leave school before fall recess begins. Is everybody okay with that? You all adults? Good. Everybody in the room? No? You want to leave early? Okay, we've got a dissension. I could do the Thursday before this, which is what? The 13th? 13th? Oh, sorry, I just yelled into the microphone. That's a month from now, exactly. So that would be week 6, 7 or so? How about that? Okay. So midterm 1 is whatever that day is, 13th. So folks who are asking me about that, that's when our midterm 1 is going to be. Midterm 2 is even more distant, so, but people still are interested about it. So you have this America week, late November.
Professor Barnes?
Yes.
There's a class right after this called Affinity that I imagine a lot of us are in that also has a midterm on the 13th.
Well, what a wonderful alignment of your studying for those 2 classes. Nah, kiddos, I'm not rearranging it because of other classes. It's the same material. It makes it better if they're back to back. Studying the same stuff. No. Not to be that guy, but like where I went to school, if all of your exams, which was all of your credit, by the way, you had 1 exam that was all of your credit. If those were all, if you had 4 of those within a 24-hour period, you just did them, and you liked it. Okay, so I just have very little personal sympathy, and that explains why I don't care Infinity. Sucks to be you all, I suppose. I have to give a midterm that evening, so I'm gonna be busy too. Anyway, America Thursday. So that's when? From the week of... Don't you hate it that the Yale calendar, it lies to you and it says, like, recess begins Friday at 8 p.m. and then it ends Monday at 9 p.m. And you're like, ooh, 12-day holiday. It's a lie. The weekends are yours already. All right, so there's the week of Thanksgiving, then there's 1 week of classes after that? And I guess y'all don't want a midterm that late. It's not really a midterm anymore. So there's the week of November starting the 7th, or we could go earlier, which is the week starting October 31st. Halloween exam? No? Halloween exam, or better yet, day after Halloween exam. So after all of those parties that you will totally don't attend, you can come to class. Okay, so some options for midterm 2 are Thursday the 3rd, Tuesday the 8th, or Thursday the 10th, I suppose, of November. What do we think? 3rd? All right, one person carries the day. What did I say? 3rd November? There we go. I'm glad it's not the 10th because that's my birthday and I have no interest in giving you an exam on that day. I would rather loudly complain about having to teach on my birthday. Can't do that within an exam. Okay, so here are those things. Please take a picture of that because this is currently the only record and I need somebody to have taken a record. Thank you very much. So, in fact, I'll take a photograph of it as well.
Will the midterm take all of class?
Yes.
If we have time accommodations, are we expected to start?
If you have time accommodations, you need to talk to me about meeting that accommodation. So I will need your form that tells me what accommodation you'll need, and I will make it work with you. I don't want to start before. Whoever asked that question, yes.
Sorry, so is October 28th also going to be?
No, that is the university date called midterm. Some unhelpful ambiguity there. Okay, we can erase this because this is Yale stuff. There you go. This is set theory stuff.
Wait, is there enough class for all classes?
I don't know, I just erased it.
It said no class October 28th.
Yeah, that's fall break.
Oh, well, great, thank you.
I feel like everybody's secretary. All right, now, I have a question. And you are really the wrong people to ask in virtue of actually being in class. Okay, but there are 70 registered students here, and there are less than 35 people in the room. Now, I personally don't care how you interact with this classroom. I missed every lecture I was ever given. I missed my first ever lecture of university because I slept in. It just doesn't bother me. But if you know someone who is supposed to be here but isn't, I'm imagining that there's people who just realized that the course is recorded and are then just like, I'm never going to get up for 9. Is that consistent with everybody's understanding of what's happening here? Oh, okay. This is the reason why your instructors don't record things, actually, because they're scared this will happen. And then it does. So tell them that they're harming you all and they need to think collectively. Okay. Those are my announcements for today. All good? Okay. So let's do a little bit of a lightning review of where we are in the course. So after discussing with folks in person and on a discussion board, I think people are confused about what the point of these axioms are. So I'm going to review them firstly, just remind you what they are, and then I'm going to talk to you about how we use axioms and why they're less scary than you think they are. Okay, so axiom of empty set says the empty set exists, right? So we could draw a picture of that as a little Venn diagram, right? And you draw a tiny little circle with nothing in it. And what do we know? Well, we know that circle exists, right? This exists. no guys in here. Okay, that's the empty set, right? Living in our Venn diagram. Pair says, if I take any two objects, I can throw those in a set, right? That's what it says. So the way I would draw that is I'd say, like, here's a set, they both exist, and so pair says, I'll do it with color so you can see what's going on. That exists, right? And then we've got extensionality, which I don't have a Venn diagram for, so it's just at the bottom, right? But it says the two sets are equal if their elements are equal. Okay, and then I got what I call weak union, which says if you have two sets, shouldn't have put my blue away. That whole set exists, right? And finally, we've got power set, which I also don't have a drawing for you. Okay, so, but I figured some folks are, let's compute some power sets together, because maybe that'll help. So the easiest set is the empty set. What is the power set of the empty set? Set of the empty set, yeah, right? So it's the power set is always the set of all subsets, right? So set of, and then we have to just list all the subsets in here. And what's the only subset of the empty set? The empty set, right? It's a subset of itself. For two reasons. Number one, everything is a subset of itself, and also the empty set is a subset of everything, right? So double reason there. But then nothing else, right? There are no other subsets. All right, and then next easiest set is the set containing the empty set. What's its power set? Oh, for Lord. That's better. So list me an element. One. Give me an element. The empty set. Any other subsets? The set containing the empty set, right? Every set is a subset of itself, right? So it's always in the power set. Right, and it gets kind of gross with all the subset symbols. So if you'll permit me, I'm going to temporarily introduce, I keep trying to draw set brackets. I'm meaning to draw 3. There we go. So let's take the power set of the set containing 1, 2, and 3. Now, I haven't told you what 1, 2, and 3 are, but they're 3 distinct objects, right? So no overlaps here. Okay, so this has a lot of subsets, actually. Can we list them off? Yes. Empty set, right? That's always in the power set. Tell me. Set containing 1, 2, and 3, right? The whole thing. Any 2 of them in a set, so the set containing 1 and 2, the set containing 1 and 3, the set containing 2 and 3, and then there's more. Tell me. The singleton sets containing 1, 2, and 3. Exactly. So in order of like size, you've got the empty set, and then you've got all of the singletons. So singleton containing 1, singleton 2, singleton 3, and then the pairs, pair 1, 2, pair 1, 3, pair 2, 3, and then the whole set, right? So this power set has 8 elements in total. Okay? And then it's not a bad exercise to write them all out, just to yourself. Okay? So that's the power set. And the axiom of power set says that I can form this collection, right? Like the subsets, they exist, and I can gather them together into a box. And that's called the power set. Okay, now, when I say these are axioms, the reason we're doing this very carefully, remember, is that initially set theory was broken and we want to avoid breaking it again. Okay, so all our axioms are doing, apart from extensionality, which tells you when things are equal, all these axioms are doing are saying sets of certain kinds exist, right? The empty set exists. Pairs exist. Unions exist. Power sets exist. So that's all you use the axioms for. If you want to, if we're doing some big set theoretic proof, and you build a new set, well, you need to know that set exists, and that's where the axioms come in. But then all of your reasoning about that set, that doesn't involve the axioms, right? Like when we computed this power set, we didn't actually refer to any of the axioms, right? We just listed all the subsets in order. And, you know, to be silly, we didn't even prove that those subsets all exist, right? We listed them, and they do. As long as this exists, we can prove the rest of them exists using, like, pair. Oh, I'm missing one axiom. Which one am I missing? Can you remember? Oh, I'm missing the axiom of subset. My bad. As long as you have subset, then they all exist. All of those pairs and triples and stuff. Okay, so the axiom of subset seemed more confusing than it is, and that's why I'm drawing these pictures. Okay, so we need, for the axiom of subset, we need a property. And I'll write it var-phi this time, so it doesn't look like the empty set. Var-phi. So this is less scary than you think it is. It is just something that can be either true or false of sets, right? So it could be contains the empty set. It could be is the empty set. It could be does not contain the empty set. It could be contains a set containing the empty set. Right? These are all properties. So what I mean is anything that you could, in principle, write down that purely refers to elements of sets. Like, that's it. So anything that you could write down, where you're allowed logic to. So you're allowed logic, and you're allowed to talk about elements. So those are your properties. So everything I just said in English, right, I could, in principle, write down in that terrible formalism that I'm trying to, like, squint at with you all. Okay, so subset says, if I have a set, then I can collect together all of the things in that set already satisfying the property, right? So I build subsets. So this is the way I visualize this. So take the whole universe, and we can divide it into two pieces. This is the piece where phi is true, and this is the piece where phi is false. Right? Everything in the universe is in one of those two buckets. Maybe those buckets are sets, maybe they're not. In fact, at least one of them is not, but that's something for later. Then we take a set A. Some of the things in A, phi is true of it. Some of the things, phi is false. And that sum could be 0, right? Like, could be none of it, right? Like, it could be completely over here or completely over here. I'm just drawing it in the middle, so that because that's sort of the general case. And the subset says that set exists, right? So I can produce subsets as long as I can describe them in terms of a property of sets, okay? So very stupidly, if we started over here, right, with the set containing 1, 2, and 3, there's a subset of it containing 1 and 3 and nothing else, right? That pair. And that subset is described by the property your elements are either equal to 1 or equal to 3, right, which is a really silly property, but it is a property. Right, and for this one, if you apply that axiom to this set, you'll get the set containing 1 and the set containing 3. Question?
I know this is probably trivial, but do we need an axiom to define numbers?
So these axioms so far will get you each natural number. It will not get you the set of natural numbers, as we'll see later. So, Yeah, so later on I will tell you, I will pick a set and I will say this will be 0 for us, right? And it will not look like 0 because you probably don't think 0 is a set, but I'm going to pretend it is. And then I'll pick a different set and I'll call that 1. And then 2 and 3 and 4, and I'll tell you how to add them and multiply them and prove all the properties you think happen about the natural numbers of our version of the natural numbers. Okay. Is that demystified or remystified? I feel that I'm sometimes at the front being like a sage who's just like saying cryptic things. And you'll just keep coming back. Like there must be something there. Okay. Where did we get? Subset. No set of all sets. Unions. Okay. Cool. So over here we have the weak axiom of union. This is weak. I want the full axiom of union now. Okay? And then we won't speak of the weak axiom of union anymore. We'll only speak of the full union axiom. But I started with the weak one because the full one is confusing. Okay, so. Where did my thing go? Over here. Okay, so weak union says I can put 2 sets together and form their union, right? I can take 2 sets and tip them into a new set. Now, last time, with a bunch of fussing around with pair and union, and then pair and then union, and then pair and then union, we found that we could take the union of any finite collection of sets, right? But unless you believe, the logic does not allow us to like take a finite process and continue it forever and imagine it completed. I can do each finite step, but I can't yet collect them all together into one big thing. Okay, so what that means is, for us, if I have an infinite collection of sets, I don't yet know how to take their union using this. Now, what I mean by I don't know how is, we all know what it should mean to take the union, right? It means we take all of those sets and we tip them into the bucket. What I mean is, our set theory cannot prove that set exists. That's all. I'm not saying you shouldn't understand what it means. I'm just saying using our axioms, we cannot produce that set. That's all. So, full axiom of union lets you do that. Okay, so it says, given a set A, there is a set B such that, and if you started the homework, you probably had to already look this up because I put it on the homework. Okay, so the idea of A is, right, everything in sight is always a set, right? So I'm going to stop saying everything is a set, right? So A is a set, and all of its elements are sets. And what I'd like to do is take all of the elements of A and union them together. That's it, okay? So A is a collection of sets. I want to produce their union. That's what our B is, and the axiom of union says that that exists. Okay, so it says X is in B if and only if, how did I phrase this? There exists an element of A such that X is in A. Okay, so you are in B if you are an element of A. Okay, so that is confusingly stated, but it literally means take all of the elements of A, union them together. That's it. Okay, so intuitively, if A is the set of, say, A1, A2, A3, potentially infinite, then what we write as big cup of A is A1 union A2 union A3 exists. Okay? Does that make sense? Cool. So this notation is quite confusing if you don't lead up to it with the weak union first. So just big union symbol A means take all of the elements of A, union them together. Okay, so union A is called the union of A. This notation is not standard anywhere out of mathematical logic, but it is very standard in it. Yes? Yes. None. So just because I can't prove a thing doesn't mean that it might not be true. So in case A is infinite, I have this. No. But if such an A exists, then its union exists. Yes, exactly. Right, if there are no such A's, then this is a stupid axiom and I didn't need it. Yes?
So this kind of like bypasses the need for reduction, right?
Well, in a certain sense, it like even writing this here, listing the elements of A one by one, is some kind of induction, right? And if A is not countable, then what does it even mean to list the elements, right? So this is, at this stage, it's purely intuitive. One can make it precise using the axiom of choice and ordinals, and we'll actually do that by the end of the class. But the idea is I'm completing the infinite version of the union, okay? So what's key, though, is that all of the sets I want to union together have to already live in an existing set, right? I can't produce the union of all of the sets at once because I cannot collect all of those into a single set, right? So this doesn't sort of allow you to take arbitrary unions. I can't just pick elements completely at random and take their union. I have to first collect them together into a set A. Okay? So it's kind of like, remember the last time, the subset axiom says I can almost do comprehension, right, which is the forming the collection of things satisfying a property, but it's I have to start with a set. This is the same thing, right? I can union a bunch of stuff together as long as I can already collect them into a set. So I can't produce a universal set, for instance. Yes?
It's just like taking off small boxes and a big box and everything.
Yes, exactly. So you take, our big box has to exist inside our universal set theory. Yeah, so we've got a big box of little boxes and we tip all of the little boxes out. Okay? But I can't just collect little boxes willy-nilly that were not themselves already in a big box. Apparently the boxes is really paying dividends. People keep using this as a helpful analogy. I'm quite surprised. I honestly did it just so that I didn't have to do real work. I could just do origami instead. But it's working out. Okay, so the axiom of union, the weak axiom of union isn't even like in the literature. This is just something we use as a stepping stone. This is us. This is our guy now. We will never speak of the axiom of the weak union axiom again. It's this. Okay, but if I want to do that, we'd better prove that I can do this using that. Right? If I want to say, number one, this is stronger, I don't have to talk about this anymore, I better be able to do this stuff. Okay, so let's say I start with a set A and a set B, and I would like to produce their old union. How can I do that using my new axiom? So I've got A and I've got B, I'd like to union them together. Tell me.
You could just put A and B together in subset C.
Yes, put A and B together first using pair. Right? So if you start with A and B, pair them together, then apply this. So this plus pair gives you the weak union, right? Because pair allows you to form those pairs first. Yeah, so that's the thing. You have to be able to like form, if I want to take the union of A and B, I have to form a set containing A and B. And then I can apply the union axiom to them. Okay, so that's union. Ugh. So dual to union is intersection, right? And if you remember last time, we did like little intersection using the subset axiom. Instead of declare, right? We said the intersection of two sets is the subset of the first set consisting of elements of the second set. Right? So you have subset, property. We can do the same thing here. So beautiful Venn diagrams. So this is our notation for the intersection of A. By analogy, right, it is the intersection of all of the elements of A. So this is, using lazy notation, it's the collection of objects such that for every element of A, oh, I'm sorry my voice is inconsistently loud. X is in that element, okay? So you're in the intersection if you are in every element of A, right? Whereas you're in the union if you're in some element of A. Okay, so this notation here, this is technically I've used the comprehension principle here, right? Like I've just described a property of sets, said that is a set. How do I know this exists? So if I want to describe a set by a property, right, comprehension, we're not allowed to use comprehension, that's verboten. So there's another strategy, which is to try and use subset instead. Okay, so we apply the subset axiom to a set that's big enough that it contains everything we want. So what will definitely contain everything in the intersection of A intuitively? Tell me. Empty set contains nothing. All right, so our goal is that the intersection of A would equal A1 intersect A2 intersect A3 intersect A4, right? That's the goal with the same A over here. So what is a set that already exists that contains this stuff? Tell me. Union of A certainly works. There's a simpler answer, though. That A? There's more than one A. That's what the big A? Not necessarily, because things in here are in an element of A. They're two sets deep. Tell me. Empty set contains nothing. I mean, union of A works, right? Right, the union of A is everything that's in at least one of the elements of A. Yeah? But we can go simpler, that's all. Which one? Nothing? No. Any one of these guys. Any one of these guys is easier, right? So you can either use the union of A, or you can just use any element of A, right? Because I'm intersecting all of those elements together. So of course it's a subset of each of those. Right? Same thing, right? Like, let me do X and Y. Right? And X intersect Y is a subset of both X and Y. So it's a subset of anything over here, right? Okay, so any of the elements of A work,
And that leads to one slight technicality, which is what happens if A is empty. This A, big A. So let's, in the case where this has no elements, which x's satisfy this property? Let's do some logic. So we've got to vote for none. No x's satisfy that property. So we've got it's vacuously true, so all. All right, so we have both extremes, no x's, all x's. Okay, so this is a fact of logic. So for this to be false, there must be an element of A, right, a little a, which does not contain x, right? That's what would make it false. But there are no elements of big A. So there is nothing to make this false. So this is vacuously true if big A is the empty set. Okay, and that would be bad, right? Because I do not want to say that the set of all things is a set. We proved that didn't exist last time. Okay, so what we will do in that case is just never ever take intersection of the empty set. Okay, so if A is not equal to the empty set, pick an element of A, and then the intersection of A are the things in that element satisfying the property. Okay. Whew. This is where the axiomatics are hard, right? Like, people know intuitively what the intersection should mean, but, it is difficult to get our set theory to do what we intuitively want it to do without accidentally building the universal set, for instance, right? We very nearly accidentally built the universal set there. Yes?
Just maybe a little bit of clarification. So there's no A, little a, sorry.
Okay, so if big A is the empty set.
Big A is the empty set, how could, say, like, the element 4, why would the element 4 be included in the intersection of big A if there's no little a element that 4 could be included into by definition?
So it's about what it means for all statements to be true if there is nothing satisfying that for all, right? So if, let me think of a good example. So if I say all humans over the age of 200 live on the moon, that statement is actually true because there are no humans over 200 at all, right? A counterexample would be a human living over 200 living on the Earth. But there just are no counterexamples, right? So for all a statement to be false means there is a counterexample, right? But they're just, if there's none satisfying the hypothesis, then there can be no counterexamples, that's all. So that's why it's called like vacuous truth. Right? It's true for a stupid reason. Okay. Cool. All right, so back of the final page, I have some exercises. So I got some sets. Can you compute them for me? And then, I don't know, is it break time? So mathematicians have this very bad habit of we never want to use something that we haven't defined explicitly, even if it helps intuition. So it really hurts me to write this on the board because I haven't told you what 1, 2, 8, and 4 are. But I'm hoping we can all just agree, for the purposes of the example, that we have that these are objects which are distinct, and I can try and compute this intersection. That was a good one. Okay, so this one, what is the intersection of this big set here? Tell me.
The first one,
Yeah.
the set containing
Singleton 8, right? Big intersection of a set is the things in every element of the set, right? So you just list out all of the elements, which are this guy, and this guy, and then intersect them, right? And so there's only one thing in all 3 of those sets, which is 8. Does that make sense? All right, so this is the same as this triple intersect this pair, intersect this pair. This is harder. So if A is a set, what is the intersection of the set containing A? Think about it. You got it? Tell me. We have a guess for A. Well, not a guess. We have a strong claim of A. Do you agree? Or disagree? I got a half-raised hand over there.
I was going to say the set containing A.
Now we've exhausted all of the symbols we're used to. So, anybody think it's the set of the empty set? All right, so let's work it out. So there's an intuitive way of thinking about it, which is if I take the intersection of a set, take all of the elements of those sets, and intersect them. So take everything in here and intersect it. So what's in there? A. So what's A intersect itself? Still A. That's the intuition, right? So this is just, intuitively, this should just be A. Now let's compute it. So by the definition, it's the collection of things in every element of our set. So what things are in every element of the set containing A? Okay, well, there's only one element of the set containing A. A. So what things are in A? Well, the elements of A, right? So the elements of A are in every element of the set containing A. It's hard to say it in words. All right, so this ends up being the original A. It's the same is true actually for the union. If you take the big union of the set containing A, you get A out as well. It could be empty. It'll never be this. I think. I need foundation for that, actually. Okay. All right, so that's intersection. So this is just convenient notation if you want to intersect a bunch of things at once and you don't want to list them out and do dot dot dots. You might have seen this kind of thing before. The union over I in some index set of A sub I, right? So it's similar to that, but this is called an indexed union. They're somewhat more complicated to define set theoretically, but we can do it. Okay, so cool. So we finally finished this first handout that I made. Whew. I mean, kind of. You can think about the question. And I have this hey what at the end, which is to remind me to say certain complicated things. I talked about that, which is properties and schemas. There is no settable sets. Oh, classes. Okay, and then are elements. Okay, so our set theory is partly about carefully determining what sets exist, right? And because we're in set theory, sets are sets of sets. Right? So everything in sight is a set. Okay, so when I draw these Venn diagrams, though, the intuition is this box is the universe of sets, right? And then inside it, I have like a set, and maybe this guy is that intersects them both, and so on. Okay, so, but this box should contain everything, right? So it wouldn't itself be a set, right? Because we proved there is no set containing everything. Okay, so the question is, what should we do about collections which are not sets, right? So this box here is trying to stand in for the collection of all sets, right? And we've proved that that cannot be a set. But it's helpful to talk about it. Okay, so there's a few different ways to do this mathematically. Number one is just talk around them whenever you want to. So whenever you want to say the collection of all sets, just say for every object instead, right? Talk about them indirectly. And that's eventually what axiomatic set theory does. A second thing to do is to say, okay, I'm going to give these a special word. And the usual word is a class. So a class is a collection of sets. Some classes are sets, but some are not, right? So the collection containing no sets, that's a class, right? But it equals the empty set, right? So that class is a set. However, the collection of all sets is not a set, so that's called a proper class. Okay, so if you want to refer to collections which are too big to be sets, you can call them classes, and that's relatively standard. But their official status in our class is they don't like exist. We speak about them as helpful fictions. So I won't reason about them. So proper classes cannot be elements of sets. They are not themselves sets. They are convenient to talk about sometimes. And finally, yeah, I won't discuss atoms or Ur elements. So I keep saying everything is a set, right? I am not postulating the existence of anything other than sets. You can do set theory with those. They're called atoms or Ur elements, depending on where you were taught these things. And you can do everything else, and it's fine. Some things are easier, some things are harder. It's just the standard set theory ZFC doesn't do it. Do you want to take a break? Let's take a break. Oh, I moved your homework due date to Friday, by the way, because folks asked. Those who are like, I would like it to be Thursday, for you, the due date is Thursday. There you go. I solved your problem. Also, by the way, there's the due date, and then there's the due date, if you know what I mean. And I don't care about either of them, so.
They don't have any like events. And the Opera House, they're starting their season. So there's
I know.
and normally if I go to New York, I go to see one of the two things. It just so happens like none of those is happening this month. So yeah. Just don't know what to do with the kids. No. They're not like especially like interesting or
Generally, it's like 2 seconds.
Whatever these five are, the union of A contains them. However, what's the more interesting question is if they said the union of this contains one. You're right here. I haven't parsed it enough. I don't know any more. If 1 and 2 and 3 are not sets, so they're just objects, then it's not great. Whenever I intersect something with the other, maybe they share those.
Oh, that is what you
It turns out
I mean, like, especially
that the union of this one and it's not obvious. It depends on how, because of how we end up defining one. It's just depends on my degree teacher
in the sense that they're really interesting, the grade is also a lot of
kosher class.
and it's not even like
It's not really, you're asking the wrong question, right? You're asking what things are in.
it's very dense and difficult philosophy of science. So it's not only about like
Yeah, so 1 and 2 and 3.
you just do it. It's kind of like you did most of it. It's an acquired skill.
Or like,
I highlight. Don't.
and I don't know if I want to.
I feel like margin notes. I'm like, this is kind of anxious. Like I have a thing. I don't use it.
The thing is, I think
The grade. It's just not helpful.
Yeah, especially.
I don't use it. I mean, the point really isn't like I don't care if I
Oh, I'm just expecting
Here's an element of that.
they're like get something out of that. Not remember what I got out of it.
I wouldn't
And if I don't, it's like
Or like, those are, I should have selected this. Those are just like, please get used to this. 3 equals wood, where you're like building sets. Maybe that, whenever you want to produce a new set, quick justification why it's twice. Not one that needs to be computer checked. I find that on no problem.
Oh, that's right.
Is it option?
Yeah. I know that it is.
Big punch.
okay, then we're gonna find somewhere nice.
Smaller.
Let's say you want to take the collection of sets containing exact
Cheese fries.
And I was like, this feels
Yeah. That's like
like
You don't
Prime Minister. You dig up a incriminating photo of the Prime Minister 20 years ago and like boom, a little bit approval rating correct. Here are like yes.
No, I want to run it.
Take criminal charges. This Canadian election is like what happened recently was Except if in mine, he, and they were already living as ministers. So he collects 60 grand to speak at an event. And then his right-hand man had to sit down.
Most does have a
Like someone had to like give up their job. Really got a big deal.
There's just a specific
You're like, yeah.
Yes, exactly, yeah.
What's there 51% of people on our page?
That not be everyone's taste, and it's also kind of small. So I don't know if it would accommodate everything.
Technically, right, I'm saying it's all things
I
that
also
are
did not.
this
Uses, it only gives you like neighbors.
it's actually determining which of these are
This morning I go
And these are just the stars, like let alone.
So I go up and
No,
I
I think this is just.
no, we tried
I'm just sitting there having full on.
Very separate.
I don't think you which is an excuse to like start it on Thursday.
I know. It's crazy. It's just weird. I remember. It's crazy. He's a cheater. I She went with her.
Yeah.
No.
I was like, oh wait, I am on this list.
Yeah, it's like almost everyone.
And then I was just organizing a dinner. Got it.
I'm so sorry.
Yeah, then we need to
Yeah.
go.
It's every day from 3:45 to in the fall, it's 20 to 25 hours a week, and in the spring, it's like up to 30 hours.
If you have her elements, then maybe you would have
It's really doesn't allow for transportation. 30 minutes to get there, 30 minutes to get back, and then also like people will take the check.
Alright, folks.
That one? Yes, it is now. Okay. So, okay. I just want to. Somebody asked a good question about this. So, if I have A is the set of 1, 2, and 3, can you tell me what its intersection is? Well, I know you know. we talked about it. Trick question. No, you can't, right? Intuitively, this would be 1 intersect 2 intersect 3. And so I'd have to tell you what 1 and 2 and 3 were as sets, right? And I haven't told you yet. So this equals something, and I just don't know what it is yet, because I haven't told you what 1 and 2 and 3 are. That's all. Intersection of this, though, what's the intersection of this? Yes, indeed. Some interpretive dance in the front row. So what are the things in every element of this guy? No things. Here's an element, it only contains 1 and 2. Here's an element, it only contains 3. There's nothing in both. Okay, so the intersection of A here is the empty set. Okay, so using the same story, the person who taught me set theory was a Jewish man, and he said this is treif and this is kosher. And that these are, there are also other, that this is morally good and this is morally evil. So we actually, some mathematicians do actually speak in these ways sometimes. So the idea is, asking this without telling you what 1 and 2 and 3 are, that's just a stupid question. Like what? How are you supposed to answer it? I don't know. Asking you this is fine, because everything's enough set brackets deep that you can work it out. Okay, so sometimes like these questions, like this question will eventually be meaningful, and I will eventually tell you what the answer is. But you can't work it out yet because I haven't told you what 1 and 2 and 3 are, right? Or at least like you can't. The intersection of A is just the intersection of A. That's the best name I have for it, right? It is whatever it is, but I can't describe it for you any more clearly. If you're Muslim, there's like haram and what's the other one? Ignorant white person doesn't know. Halal. Halal and haram. There we go. Fit to whatever your religious background is. Mine is tediously Christian. So, not that anybody asked. All right, so we have, what axioms do we have so far now? Okay, so we have extensionality, empty set, pair, full union, power set, subset. Right? That's what we have so far. There are some more axioms, and I would actually like to tell you what they are now, even though you're not allowed to use them yet. Ooh. Because I will keep referring to them, and if I don't tell you what they are, it's kind of mean and mysterious. So those axioms are infinity. I have to remember enough stuff in my head. It's replacement. Regularity. Choice. I think that's all of them. This is off the top of my head. Please go look at what ZFC is on Wikipedia and it will tell you if I missed anything. So what does infinity say? I'm not going to tell you in detail because we haven't got the definitions yet, but this thing says the natural numbers exists as a set. Okay? That's what the axiom of infinity says. It doesn't just say an infinite set exists, which is weaker. I think just by itself, that would actually not be what you want. I think not even with subset. We need other axioms. Replacement is, this is the axiom that's so obvious that Zermelo he forgot to write it down. So if you look back in the history, right, what we're studying here is called ZFC, which is Zermelo-Fraenkel set theory with the axiom of choice. Z by itself is ZFC, except he forgot that this was necessary. And then later, Fraenkel was like, oh, you need this. And he was like, oh, yeah, I do. Right? So what this says on an intuitive level is the following. If you have a description for a function, right? So functions are things that take in an object and spit out a unique object, right? And you have a set, then I can think of that set as the domain of the function and apply it pointwise and get the range, and then the range is a set too. So it's called replacement because you have this rule that allows you to take an object, x, and then like replace it with f of x. So if you have any set of objects and you have something that looks like a function, then the set of all f of x's exists. So that's called the axiom of replacement. I think it's somewhat surprising that you need this because after you've been playing with sets for a while, it seems quite intuitive. Like if I have a set and I can describe, and I think of those as x's, and then I've got a corresponding collection of y's, it seems that the collection of the set of y should exist. Okay, but anyway, that's what replacement means. And also, description for a function is self-vague. Yes?
Is that not extension?
No. So it says given x and a function, then the set of f of x such that x is in x exists. Right, so that's talking about a set existing, which doesn't have anything to do with extensionality, right, which talks about equality. This is roughly what it says. Being more precise about it, I have to tell you what I mean by like description for a function, and how you write this down, and so on. So that's replacement. We'll use it like one time to get the universe off the ground. Regularity, this is the axiom that you'll all want to use all the time, and I refuse. I call this foundation. And other people do call it that too, but I think regularity is more common. Okay, so what this says intuitively is no x exists. Oh, It says no set is a member of itself. Oh, there we go. It's just x in x is impossible. Okay, and it's actually stronger than that. It implies that, like, you can't have x in y in x, right? It can't live, like, too deep and x in y and z in x. None of those loops can exist. And it's actually stronger than all of those claims at once. So it actually tells you, formally it says that the element symbol is well-founded. We will define what that means much later. But roughly speaking, this means that no set is ever a member of itself. You are not allowed to use this on your homeworks, ever. Okay? This is a stupid axiom. I don't like it. It's never used ever. Like, never in the world is this ever used. So it's just there because people don't like the idea of sets being in themselves. There's no mathematical reason for it to be there. This is the big one, choice. So choice says, if you have a collection of buckets, and each of those buckets are non-empty, think sets, then you can choose one element from each bucket. And you're like, okay, why do I need that as an axiom? Okay, well, the idea is, if you have a finite number of buckets, actually our set theory is strong enough already to prove that I can choose one at a time. If I have infinitely many buckets, I don't know how to choose. Here's an example. Suppose you have infinitely many pairs of shoes. Now, there is a way of describing a process of picking a shoe from each pair, because I can always pick the left one, right? That describes a process. Now suppose you have an infinite collection of pairs of socks. Can you describe a process that picks one of each pair? And the problem is, like, no, because they're indistinguishable, right? Left sock and right sock are the same. So to choose one sock from an infinite collection of pairs, you need to make infinitely many arbitrary choices, right? I just need to pick one and pick one and pick one somehow. If I have shoes, I have to make infinitely many non-arbitrary choices, right? I can tell you how to do it. Okay, so the axiom of choice says, if you ever want to make infinitely many arbitrary choices, you can do so. And people really don't like this axiom, well, some people, like in the 30s, because it implies some very, very strange things. For instance, it implies that you can take a three-dimensional ball, cut it into 5 pieces, and rearrange those pieces into 2 balls of the same size. As the original ball, by the way, not as each other. Okay, so that's a very unintuitive claim. It's called the Banach-Tarski paradox. But if you don't allow choice, then some other weird things happen too. Okay, so that's the axiom of choice. It's the thing with the buckets and the socks and the shoes. Okay. And this, yeah, people worry about this because mathematicians in previous centuries they really wanted everything to be non-arbitrary wherever possible, right? You shouldn't be able to make like random choices essentially, and this is like highly non-random. It's highly non-deterministic. All right. So now you know what those are. You're not allowed to use them yet. It's like Christmas, and I let you like shake the boxes of your presents. Or your birthday. I don't know. Insert a holiday where you get presents. I don't want to be Christian-centric here. It's just look what my religious upbringing has done to me. And I'm having a crisis up here about like, anyway, let's move on to notes 3. So what are we doing? Pairs. All right, so we finally have enough axioms to actually start doing some math. So we're not going to introduce any more axioms for a while. I guess I've introduced all of them, but we're not going to need the new ones for a long time. So we're going to actually start building some mathematics now. Okay, so what is the thing that is always in mathematics? No matter what class you take, what do you do? And the answer is you apply functions to things. In every math class, there are functions, right? Calculus is about smooth functions. Analysis is about also smooth functions. Algebra is about functions between different objects, right? Like if you took linear algebra, we have linear functions, right? If you took abstract algebra, you have homomorphism. You take topology, you have homeomorphism, right? In fact, mathematics is kind of more about the functions between objects than it is about the objects themselves. Look up category theory if you want to know more about that. Okay, so what I would like to do is produce something that looks like functions purely out of sets. Okay, so that's our goal. Build to functions. Okay, so firstly, if I want to build to functions, I have to talk about input-output pairs. That's what functions are, right? They take an input, they spit you an output. So I need to be able to determine sort of between an input and an output, and the way we do that is through an ordered pair. So we want an ordered pair. Okay, so an ordered pair is just two things, but I know which one's first, right? That's all an ordered pair is. So I have this thing that I call the characteristic property of pairs, and I think that's a really good name, and everybody else should adopt it. So I put it in the notes, I put it in the homework, and when you all go out into the mathematical world and become working mathematicians, you shall spread it too. And that will be my contribution to the world. Okay, so the ordered pair of A, B, I'm going to denote with angle brackets to keep it distinct from parentheses and set brackets. Okay, so this is going to be our ordered pair AB. So I want a set that represents this, and it should have this property. If two ordered pairs are equal, well, that's the same as saying their first coordinates are equal and their second coordinates are equal, right? So this is what I call the characteristic property of pairs. So if you're a pair, then being equal is the same as your first coordinates being the same and your second coordinates being the same. All right, so now the question is, so if I start with A and B, little a and little b, how can I build a set in terms of A and B, presumably, which has this kind of property? So let's look at some examples that don't work first, and then you'll see like why this might be important. So example 1, or non-example, I called pair and then U for unordered, as you'll see shortly. So this pairing convention suggests, okay, for the ordered pair in A and B, just pair A and B together. Now, why does this not satisfy this? So the way sort of to break this, one direction here is trivial, like down, this is always true, right? If A and B are equal, then the pair AB equals the pair AB, no matter what pairing it is. So the interesting direction is this way. So it says if two pairs are equal, then their first coordinates had to be equal to one another, and their second coordinates had to be equal to one another. So to make that false, we need to produce two different pairs, two pairs which equal the same as a pair, but which do not have the same first coordinate and the same second coordinate. Tell me. Yeah. The trick here is that this doesn't respect order, right? Right, so the pairs are equal, but their first coordinates are not equal, and their second coordinates are not equal, right? Unless A equals B. So this does not satisfy the ordered pairing convention, right? Because I can't distinguish between first element and second element using this, right? Sets have no notion of order. So we're going to have to somehow mock one up. All right, so here's a harder one, which I'm going to make an exercise. I called this pair sub f. F for fails, because I couldn't think of a name for it. So it's the pairing convention that fails.